A superconducting magnet is a electromagnet made from the coil of the superconducting wire. It is nothing but a superconducting magnet is a magnet which is made by the superconducting wire. They must be cooled to this cryogenic temperatures during operation. It must be cooled due to this cryogenic temperature. In its superconducting states of the wire can be conduct much larger electronic current than this ordinary wire. In the superconducting conductor that can produce a large number of the electric that a normal electric wire can do, creating intense magnetic field. Superconducting magnet can produce the greater magnetic field that all but the strongest electromagnets and can be cheaper to operate because no energy is dissipated as heat in the winding. They were used in MRI machine in the hospital and scientific equipment such as this NMR spectrometers, mass spectrometers, and particle accelerator. This is used MRI machine, magnetic resonance imager machine, NMRI machine, resonance, nuclear magnetic resonance spectrometers and mass spectrometers, particle accelerators, etc. During operation and magnetic winding must be cooled below their critical temperature, the temperature at which the winding material changes from this normal resistive states and becomes a superconductor. Two types of the cooling regimes are commonly used to maintain the magnetic winding at temperatures of sufficient to maintain the superconductivity. That liquid cooled.
Hello friends. When an electric current is passed through a conductor, some of the energy is lost in the form of heat and light. The amount of energy lost varies depending on the individual material's electrical resistance. Some materials, like copper and gold, are great conductors of electricity and have very low resistance. Scientists discovered that the colder these materials are, the more conductive they become. But no matter how cold you make copper or gold, it will always show some electrical resistance. Mercury, however, is different. In 1911, when scientists cooled a sample of mercury all the way down to 4.2 degrees above absolute zero, its resistance abruptly disappeared. The first superconductor had been discovered. Gradually, more and more superconductive materials have been found that show zero electrical resistance below a certain critical temperature. And when resistance is zero, electricity is conducted perfectly without any loss, and a current can theoretically flow in a closed loop forever. This has been demonstrated by scientists who have sustained electrical currents in superconductive rings for years without any measurable depreciation of energy. And it doesn't end there. Not only do superconductors have absolutely zero electrical resistance, they also don't like to let magnetic fields pass through them. Instead, the field remains at the superconductor's surface. This expulsion of magnetic fields is known as the Meissner effect. You've probably seen the Meissner effect in action in science experiments that look like this. A magnet is set on top of a superconductive material, and at room temperature, nothing really special happens, but when the material is cooled down to its critical temperature, the Meissner effect kicks in, causing the magnet to levitate, as if by magic. But superconductors can be used for much more than cool science tricks. These materials are used today in MRI machines, super fast floating trains, and even particle accelerators. But we can't forget that these superconductors have to be kept at temperatures near absolute zero in order to function properly. This is a main limiting factor in the practicality of superconductors. Fortunately, scientists have been busy finding and creating materials that become superconductive at higher and higher temperatures. For example, some ceramic materials undergo a superconducting transition at high enough temperatures that they can be cooled down using relatively warm liquid nitrogen. These materials are known as high-temperature superconductors, and they have revolutionized how and where we are able to use this technology. But still, always having to have liquid nitrogen at hand is extremely limiting. The goal for scientists is to create a material that is superconductive at room temperature. If we have room temperature superconductive wires for electronics, we'd be able to power devices using much less power. None of the energy would be lost as heat, changing the way the electronics are designed and built. This technology would allow for smaller and much more efficient devices. In 2015, researchers observed a material that, when placed under extreme pressure, became superconductive at around -70 degrees Celsius. This set the record for the highest temperature superconductor, but as of now, room temperature superconductors haven't been found. Well friends, you know what to do if you feel this video has earned your support. If you're a fan of science, maybe you'd enjoy some of these other videos that I've made. A big thanks to my subscribers, both old and new, for inspiring me to continue making videos. Thank you for making it all the way to the end of this video. I sincerely hope you enjoyed. My name is Randy Dobson, and I'll see you next time.
TC and the 18 Kelvin operating and this 42 Kelvin is able to withstand a much higher magnetic field intense up to the 25 to the 30 Tesla. Unfortunately, it is a far more difficult to make the requirement filament from this material. This is why sometimes a combination of this MB3SN for the high speed field selection and this NBTI for the nuclear section. This sections is used for this vanadium gallium is another used for this high field intense. Higher temperature superconductors may be used for this high field intense required magnetic field higher than NB3SN can manage. WCO magnetism's idealization also used to be current field and conducting high current from the temperature into this gold magnetic without any compromising the large heat leak from the resistive slits. The coiled winding of the superconducting magnet or made the wide tap from the step to superconductors and titanium 2 wire of time itself made with tiny filament and micrometer thickness superconductor of this copper matrix. The copper is needed to add the mechanical stability to provide a low resistive path for the large current to the temperature rises TC and this current rises IC, which superconductivity is lost, and these filaments are needed to those small element. Because of this type of these superconductors and this current only the flow skin deep. Supply operation. This current of the coil winding provided by the high current, very low voltage DC power supply. Since it is steady to it is also DC power supply. Since it is steady state only voltage across the magnetic due to this resistance of this Wheeler wire, any changes of the current throughout this magnet must be done very slowly. First, because the electrically this magnet is large inductors and abrupt current changes will result in the large voltage spike across this winding. The more importantly, because the fact changes in the current can cause eddy current and the mechanical stresses in this winding that can be participated a quench, so that the power supply is usually microprocessor controlled, programmed to accomplish the current change gradually. Its gentle ramp. It usually takes several minutes to this de-energize the laboratory seized magnet. Persistent mode. This all operations made used by this most superconducting magnet is short circuit winding in this piece of the superconductor when the magnetic has been energized. The winding became the closure of the superconducting loop and the power supply can be turned off. This persistent current will flow for this month perceived to the magnetic field, and the advance of this persistent mode, that is stability of this magnetic field, is better than the achievable and with this best power supply. This is no energy is to needed to the power winding, and the short circuit is made by the persistent switch in the piece of the superconductor inside the magnetic connected across this winding ends and attached to this small heater. When this magnetic is first turned on, the switch to the wire heated above this transition temperature so that it resistive. Since the winding itself has to no resistance, no current flow through the switch wire and to go to the persistent modes, and supply current to be adjusted until the desired magnetic field is obtained, then the heated is turned off. The persistent switch cooled it to the superconducting temperature, short circuiting the winding, and the power supply can be turned off. The winding current and the magnetic field will not actually persist forever, but will recede slowly according to normal reductive and NRMS systems timely constant, where it is a small residual resistance for the superconducting winding due to the join of the phenomena called the flux motion resistance. Nearly all commercial superconducting materials are equipped with this persistent switch and magnet switch. A crunch of this normal terminations of the magnetic operation that occurs when this part of the superconducting coils enter a normal state. This can occur because this field inside this magnet is too large and the rate of changes of field is too large, and this eddy current and current of the heating of the superconducting of the combination of the two is very largely emulative systems. And this magnetic resonance measures how it is work. Is a superconducting magnets have a number of advantage over the resistive electromagnets. Superconducting magnet have a number of advantage over the resistive electromagnet. They can generate magnetic field that are up to 10 times stronger.